summary of what we looked at in this chapter. So we were interested in trying to define and refine our current understanding of models of our atom. Right? Now remember, none of us here, myself included, have ever seen atoms, nor will we ever see them. They're just too small. Right? They're smaller than the waves of which we can see them. And when we use waves that are the same size as atoms, we interfere with the atom itself. We change its energy. And so Heisenberg kicks in at that point. Well, that didn't stop people from trying. So J.J. Thomson, he invented a very specific, specialized cathode ray tube, where he had cathode rays traveling through a tube, passing between crossed, perpendicular, magnetic and electric fields. And so he was able to show, number one, that cathode rays had a speed that was not EM wave speed, so they were not light or anything like light. And he was able to show that they were charged particles with a specific charge to mass ratio. So cathode rays were very small, charged particles common to OMAC. That's what he did. He came up with this plum pudding model of the atom, where the atom was believed to be a cloud of positively charged matter with small, confined, negative charged particles, we know them as electrons today, interspersed throughout. So that was the start, just over 100 years ago. Along the way, we met and learned how to work with mass spectrometers, where we take very small quantities of matter, we ionize them, we accelerate them, we select for their velocities, and we can figure out that different masses will be deflected different radiuses. And so we can calibrate an instrument to look for the amount of bending of these particles in a magnetic field. All right, least massive particles, okay, are easy to deflect. More massive particles are harder to deflect. And so we know by how many are going here what the composition is. There's some of the physics involved in all of this, and we did practice it, and you should continue to do so as part of your review. Then we went to Millikan. Millikan filled in the other piece of the puzzle about the charge of these cathode ray particles, soon to be called electrons. Injected tiny, tiny particles of matter randomly charged between two parallel plates, balancing the electric and the magnetic fields. For suspension or moving at a constant speed, it's actually true for both cases. F electric and Fg are equal and opposite. EQ is mg. So Q is equal to mg over E. If the drop is accelerating, that's no problem. We just add a net force into the mix. We still come up with a Q, which is ma minus mg over E, keeping the direction in mind. And finally, in every case, the number of electrons is the total charge divided by elementary charge. Interrupt me at any time if you have questions. Then we went into Rutherford and his scattering experiments to help further define the model of the atom. And so what he observed was that alpha particles passing through the atom will deflect strongly from a center charge location, giving him a scattering pattern that looked like this, and helping him pin down the idea of the nucleus in the planetary atom. He used conservation of energy, kinetic to electrical, to help figure out the radius of the nucleus. And so you should be prepared to do the same thing. We went into spectroscopy briefly, and we learned that every element vapor or gas will produce when excited an emission spectrum, a series of very well-defined lines of light. And these lines of light, as it turns out, are unique for every element that we come across. Hydrogen had 4 visible lines representing electron transitions. We now know that light is produced, all light is produced by down